Now this is a type 2 superconductor, and what that means is that it can actually undergo quantum locking. But in order for it to become a superconductor, we have to cool it down. Now I'm just going to drop my superconducting puck in here. Watch this. Notice how it's not touching, but I can push the superconductor by touching the magnet. It's like it's gripped onto it. Okay, now let's try it with a few more magnets by putting the superconductor on top of them. Look how it just stays right where I put it. So cool. So now I'm going to place it on this track that just has rows of neodymium magnets so that these are opposite poles. So what it does is it creates a symmetric magnetic field in this direction, but not in this direction. Now watch what we can do. Now, as if that's not impressive enough, let's flip the track over and watch this. So the superconductor is so strong it can actually carry other things on it. So let me explain how quantum locking works. So how we can get the superconductor to start flowing current in it is just move it towards a magnet. When you move it towards a magnet, it exposes it to a changing magnetic field. And when you have a changing magnetic field, that induces a voltage, and that voltage pushes electrons around in eddy currents in the material. That's the reason why when you move like a block of aluminum towards a large magnet, then that aluminum will slow down. So it's like it's moving through water or something, because it's causing small eddy currents to form in there, and that movement of electrons in there causes a magnetic field that opposes its own magnetic field that it's going through, and so it pushes against it and slows it down. So what that means is that when I move a superconductor towards a magnet, it's going to repel it. But that's not all we saw there. So in a normal conductor, let's say we had a sphere of aluminum or copper or something, and this is our superconductor. If you could measure the magnetic field lines around it when you put it next to a magnet, this is what it would look like for a metal. The magnetic field lines just go right through it. But what's interesting for a superconductor, that's not what happens. Because the superconductor is forming these eddy currents in there when you move it towards the magnet, it's opposing the magnetic fields in there, and so it doesn't let any magnetic fields form in there. And this is a form of perfect diamagnetism, but it also is called the Meissner effect. So they go right around it. The magnetic field lines can't penetrate it, so there's no magnetic flux in the superconductor. Now this is a result of superconductivity, but this still isn't quantum locking. We're almost there. So this is a type 1 semiconductor, but what I have here is a type 2 semiconductor. Now type 2 semiconductors don't quite look like this. Type 2 semiconductors actually have impurities in them, and these impurities allow some magnetic fields to penetrate it. It can't move through these magnetic fields because it gets locked into place. The magnetic field is funneled down through the center and it locks it. So in order to move through it, it has to push through those impurities. And so the only way it can move through a magnetic field is if the magnetic field is symmetrical, because then it just gets replaced with a new part of the magnetic field, and so it doesn't matter where it is in that field, it can just move through it. But any magnetic field that's not symmetrical, it can't move through it. So basically it's like it has these strings going through it, holding it in place. They're kind of like these magnetic strings that don't let it move. So in my experiment, I could move it like this on the track because it was a symmetrical magnetic field. And so it didn't matter where it was in the magnetic field. It didn't affect the lattice inside. There was no internal force on it. But when I moved it up and down, that wasn't symmetrical. That was changing the magnetic flux through it. And so it pinned it in place. And so quantum pinning is actually due to parts of the superconductor that aren't superconductive. And it makes a part of it that gets pinned in place due to the magnetic flux that's able to penetrate it in a few spots. It's actually more than a few spots, it's actually a few billion spots. So how this differs from a normal repelling force of a magnet is it's actually not repulsive or attractive, it's both of them. It just wants to stay in place no matter what. And so you can put it in anywhere you want and it'll stay there. And thanks for watching, and I'll see you next time.